Well, yes, just start it now. Yeah, good. The participants are coming in. Welcome, welcome. So I suggest to still wait a little bit in order to give a chance to more people to come in. Because it's only 1 minute after time, so we can still wait a little bit. I'm having a look at the list. 40. Mm-hmm. Maybe if you like, you can already share the title slide.
Sure.
Mariagrazia. Mm-hmm.
Can you see it?
Yes.
Nearly. Yes, excellent.
Okay.
Just a few minutes more. Look, 45. So we are nearing the point where I am going to officially open the session. I'm just having a look at who's there.
Mariagrazia, I'm seeing your slides are switching the modes between the presentation mode and the non-presentation mode.
They should be in presentation mode. They're moving?
They are, but when you change slides, yes, it looks a bit weird.
It should be fixed to the first page.
Now it's fixed.
Oh, I see the first page, but when you change pages, we briefly see the editor.
Oh.
Now it seems okay. Now it's okay.
Okay.
Well, when it is static like that, it's fine.
Okay. You tell me if there's any issue. Otherwise, I get out of the presentation mode.
Can you just move a bit between slides just to see how it looks like?
This is the second slide.
Yes, that's fine.
Ah, yes. And there is an effect of fading.
I don't see any blinking now.
Fading. Can you move a bit again, please? Just to.
Fourth slide.
When you move between slides, sometimes I see in a glitch the PowerPoint. I don't know why, but well.
Mysteries of Microsoft.
Yes,
right.
Some kind of glitch. But when you are in a slide, then it looks good. Bon.
Yeah, I think that's fine.
Okay, so we are nearing 5 minutes beyond schedule, and we are nearing 50 participants. So I'm going to start. Welcome, everyone. Good morning, America. Good afternoon, Europe, and good evening, Asia. Because as we already noted, there is a wide range of time zones concerned. But it is one of the interesting effects of this series of seminars that we, I mean, it didn't exist much before this sanitary problematic times, that we had that kind of wide area virtual seminars. So it is an interesting phenomenon. It's a pleasure and an honor for me to chair this session because I found it to be a very good idea, mostly by Anne-Catherine and Kai, I must say. And so this is the month of May edition of this seminar, which will be consisting of a approximately 40-minute presentation, followed by discussion and questions. So participants, if they have questions, are invited either to wait until the end of the presentation, or they can write it in the chat if they like to note it before the end. And we will go through the chat and check questions. So it's the best way to interact. And following the discussion, there will be, as in the previous editions, a time where we will have breakout rooms where the people can discuss in small groups. We will be doing groups a bit randomly, but you are free to come and go, of course, as you like. So the speaker today, which I am very happy to introduce, is Mariagrazia Dotoli, who is a full professor at the University of Politecnico di Bari, teaching systems and control engineering in the Department of Electrical and Information Engineering. And her special interests are the modeling and management and control and automation of discrete event in industrial systems involving Petri nets as a modeling tool. She is associate editor of several IEEE transactions on automation science and engineering and control systems and technology, amongst others. She is the general chair of the Mediterranean Conference of Control and Automation this year. And she's going to make a presentation, which is a tutorial and survey on Petri net models for logistics and transportation systems. Mariagrazia, please.
Thank you, Eric. Thank you so much for your kind presentation. So I would like to thank everybody for attending this talk, and I would also like to give a special thank to Kai and Anne-Catherine for inviting me to hold this talk again. It's my great pleasure to be here. And so the idea is to present for about 40 minutes, and then in the end we can have a discussion if you have questions or suggestions, or you want to talk about this subject. I also would like to mention that this is a joint work that I have done with Professor Carla Seatsu from the University of Cagliari, and with Dr. Graziana Cavone, who is a researcher in our lab, the Decision and Control Laboratory at Politecnico di Bari, and she is also present. She will also be present during the presentation. Here you can find also in the slides that I've also given to our colleagues, and so you will be able to see them later on. You can find a link to our lab where you can find also a lot of material related to this presentation, and my email is also in the slides. So the idea today is to talk about how Petri nets can be used for modeling and control of logistic and transportation systems, again with a focus on freight transport. And I would like to present a bit what has been done in the related literature, and also what we are doing in our lab, again thanks to the help of Carla Seatsu and Graziana Cavone. Can you see my second slide now?
Yes, now voila.
Yes.
Now we see.
Okay, good. There is a bit of delay. So this is the outline of my talk today. I will give a little introduction about the motivations and objectives of the talk, and then I will discuss the main contribution, which is classifying the works that use Petri nets to address freight transport decision problems. And I will also provide some examples of applications, including some real applications of an intermodal terminal that we have here in Bari, where I live. And then I will draw some conclusion and will give some suggestions for future works. We are talking here about freight transport again, and as we all know, transportation has an important role in economy and the society. It has a large impact both on growth and employment, so it is an important subject. If we refer to the EU, but the percentages are similar also to other countries, especially Occidental countries, the transportation industry accounts for 5% of the gross domestic product, and in particular in Europe, it refers to 10 million people employed. Also, if we consider logistics account for about 10 to 15% of the cost of a finished product for European companies. So it is a significant issue. And therefore, it's obvious that effective freight transport and logistics systems are fundamental for companies. Recently, we know that there has been the development and the growth of intelligent transportation systems, which lie at the integration between transportation and information and communication technologies, and they can really sustain the competitiveness and adaptability to market changes of companies, thus helping them to increase their productivity. So what is the idea? The idea is to talk about how Petri nets can be employed for modeling and control of transportation systems. In fact, as we all know, Petri nets are a discrete event formalism that is quite general, and they can efficiently capture practical situations of a very high number actually of application areas, including actually transportation and logistics systems. So the aim of the talk today is surveying literature contributions that use Petri nets for freight, logistics and transportation to address the related modeling and decision and control problems, trying to classify the contributions that are available and the tackled problem, providing an overview of the viability, contribution and eventual limitations of the approaches that exist, and finally possibly identifying open issues and future research lines. Sorry, and I forgot to mention that a lot of the concepts that I would talk about are available in this paper that is referenced here on the bottom. Let's see if I can. Yes, here. So it's a paper that has been published a few years ago in the IEEE Transactions on Intelligent Transportation Systems, and has been authored together with Carla Seatsu and Graziana Cavone, as I mentioned earlier. So why Petri nets? Petri nets are a general discrete event system formalism, so they can be applied quite efficiently for representing freight, logistic and transportation systems, and they have several advantages. First of all, their graphical aspect, which allows understanding easily the system, but they also have an underlying mathematical structure, which is very useful, of course, when we want to study the actual characteristics of the systems. They are scalable, they have the characteristic of modularity, they are quite versatile, and they can be employed for simulation. And this is useful both for studying the performance of the system, but also for applying some control laws. I have included in the slides a few hints about Petri nets, because I think this is the first talk about Petri nets. So please bear with me if you already know all this, but I wanted you know, the talk to be self-included. So Petri nets are basically bipartite graphs. They are composed of places and transitions. So places are represented by these empty circles here, and transitions by bars. So we have a finite set P of places and a finite set T of transitions, and we have tokens that are these black dots that flow in the net, and places and transitions, they are connected by arcs, and these connections are modeled by the pre-incidence matrix that models the arcs from places to transitions, and the post-incident matrix that models the arcs that go from transition to places. The Petri net is also, the generic Petri net is also characterized by marking, which is a mapping from the set of places to n to the power of m. And the token is a basic element that flows in the network and allows to graphically represent the marking of the net. So here we have a very simple example, a network, a Petri net with two places, x and y, and two transitions A and B. We have a marking that is 2, 0, because we have two tokens in the first place. And pre and post are the two pre-incidence and post-incidence matrices represented here. So the evolution of a Petri net produces a new marking, which can be actually computed by a state equation that updates the previous marking, M0, into the actual marking M, thanks to the term C sigma, where C is the incidence matrix, which is simply the difference between the post and pre matrix, and sigma is a firing vector that is relative to a firing sequence, and its generic component is equal to the number of times that the generic transition appears in the sequence. A transition is said to be enabled, and so it can fire if the input places of the transitions have a marking, so a number of tokens that is higher than or equal to the weight of the arcs in input to the transition. So again, with reference to the example before, we see that both transitions A and B are enabled because there are two tokens in place X. And if we consider a firing vector 0, 1, so we have a transition B that fires, we get a new marking because we get one token that goes from X to Y, like in this figure here. And so the marking of the net is updated thanks to the equation that we wrote before. So how can we use Petri nets for transportation systems? Places may be used to represent basically the system resources. So for example, a crane, but also the capacities of the resources. So for example, the capacity of a yard, and also some conditions to synchronize or assign priority to events. For example, the availability of a mean of transportation. Instead, transitions, they really represent the event in the system. So they can be stochastic, deterministic, or immediate. Stochastic transitions model input flows and in general activities of transportation means. So for example, the arrival of a truck at the terminal. They can be deterministic if they are referring to temporally well-defined events. So for example, the unloading of a container, and they can be immediate for instantaneous events. For example, if we want to model some communication signal that is transmitted instantaneously, at least from the point of view of the time constant of the system, of the transportation system. And then of course we have tokens that flow in the system, and they typically represent transportation means, capacity of resources. So for example, trucks, cranes, operators, and available space in parking areas, and so on. If we look at the related works in the literature on transportation using Petri nets, actually we find a lot of material in the literature, but this material is typically falls into two different categories. So the main categories is for manufacturing systems. These are, of course, the oldest systems that have been modeled by Petri nets, and then later on supply chains. So all the modeling of the internal logistics are typically modeled by discrete event systems, and then including Petri nets. And also you can find a lot of works that deal with urban transportation, and in particular passengers transfer. I myself with my group have worked in this. For example, here you see a Petri net representing a traffic controlled intersection, actually also in the city of Bari. And this was published in 2005 in Control Engineering Practice. So these kind of papers typically deal with public transport, traffic lights, road traffic, urban traffic systems, and so on. And here also in the slides, you can find some seminal papers that you can study regarding these areas. Instead, what I want to focus today is on freight, logistic, and transportation systems. So transportation, not of passengers, but of freight. In general, it is possible to find a fewer number of papers on this topic. And there are some surveys that either talk about supply chain management, so again, specifically on manufacturing, or that use Petri nets for a specific transportation mode, but not in general for transportation. So instead, what we did in this paper that was published on the transaction on intelligent transportation systems was classifying the papers on freight transport, and we have updated this classification until today on freight transport. So it's about more or less 125 papers, of which around 80 papers are on journals and half of that on conferences. And the first thing that you can do is make some classification. First level classification and obvious classification refers to the freight transportation mode. So of course, there are papers on using Petri nets for freight transport using waterways, air, rail, road, pipelines, and then mode combinations. And finally, it was interesting also to consider the interterminal handling that is done by automated guided vehicles, which is also an important subject. A second level classification, of course, can also be done referring to the decision-making level. In particular, there are problems that are considered as the strategic or tactical level, so I would say with a medium or long term, and then operational level or real-time problems that use this formalism. A third level of classification refers, of course, to the type of Petri nets that have been used to tackle the problem. And here we can refer basically to three different classes. So logic Petri nets that employ time, so time Petri nets, and also high-level Petri nets like colored, hybrid, or fuzzy Petri nets, and so on. There are many types, as you probably know. Another interesting classification that can be done with this type of contributions refers to the main research areas that are studied and that are directly related to the strategic and operational decision problems. So I would say that the main areas of research are, one, referring to the resource planning and performance evaluation, and second, to the monitoring and control of resources. And here there is a particular interest, of course, in safety and liveness assurance. So if we consider the first transportation mode, that is regarding waterways, so ports or also rivers, evidently, the first important class of problems that has been tackled is the problem of port container terminals decision problems. And these can be classified into strategic, tactical level problems and operational level problems again. The subjects that have been addressed in the literature are modeling and analysis of port terminal workflow, resource planning and performance evaluation, collision avoidance, and then also the study of the port terminal capacity management. With a reference instead to operational level, there are problems such as optimization of resources allocation and optimization of container stacking. And here, for each class, we have provided a chart, a pie chart that allows you to understand what are the main problems that are tackled. So in this case, strategic problems are definitely those in which literature is most interesting. And here you can see all the types of Petri nets that are used. So place transition nets, deterministic time Petri nets, stochastic, generalized, and colored. And then again, if you then have a look at the paper that we've written, you will find a lot of details for each problem, and then you can consider all the references that we have included in the bibliography and, of course, study them. What is interesting also to see is the distribution of these papers over the years referring to waterways. And as you can see, there are not many research works on this type of problem. And actually most contributions where we find ports in particular, they refer to combined modes of transportation. So they can be classified under intermodal transportation. And I'm talking about that later. Also considering waterways, a second area of problems are those that refer to the single transportation means. So here we find fundamentally only operational level problems, and they refer to automatic traffic control vessels, energy control systems, and the optimization of ship maintenance. Here you see the type of nets that are employed, and again, only a few papers published exactly for the same reason that I mentioned earlier. So this was for waterways. And summing up, what is interesting to say is that regarding the two areas of study, so resource planning and performance evaluation and monitoring and control, we can say that logic Petri nets can be used to represent workflows in port container terminals. They can be used to strategically evaluate the efficiency of the system, referring to some particular performance index, and of course, analyze and prevent deadlock using structural analysis technique. Instead, when we want to take time into account, of course, we have to use timed Petri nets. These can be very effectively used to perform realistic simulation of the system, to evaluate some performance indices that take into account time, and also, most importantly, to identify eventual critical resources that may generate bottlenecks in the port container terminals. However, we still have the possibility to use high-level Petri nets. So, for example, color Petri nets, they are used as an alternative to mathematical programming for monitoring and control resources. And a seminal paper that you can study is this paper here by Legato, Trunfio, and Meisel that was published in 2012 on computers and operations research. What is still missing in this area is the study of the management of emergency situations in real time with Petri nets. If we move to air transport, we have, of course, a similar classification as before. In this case, we find even fewer contributions regarding to the operational problems, and basically they refer to maintenance modeling and simulation. Instead, from the strategic level, we can see applications to the traffic capacity and management in airports, aircraft operations modeling and verifications, and of course the modeling and simulation of airports. I would like also to mention here that a particular class of Petri nets have been proposed for this, that is called agent-based mobile Petri nets, together with other more classical formalisms. Here you see the published papers that are kind of getting up later, but again, there are also in this transportation mode, there are not many research works, and probably the reason why this happens is that most works address passengers transportation. There is really a lot of contributions of that, but many less for freight transportation, so for cargo. And what we can say in general for this class of problems is that regarding monitoring and control of resources, there are really no contributions yet. So of course, a future research path is to try and use Petri nets for monitoring and controlling these of systems. Instead, with reference to resource planning and performance evaluations, time Petri nets have been effectively used to tackle safety and liveness, and to study the performance, and also to perform structural analysis of this kind of net. Finally, colored Petri nets have also been used to plan and analyze terminal traffic, and also consider aircraft maintenance. And the paper you can study on this is a paper by David Raju and Bishan that was published in 2011 on expert systems applications, which is quite interesting. So this was for the second mode of transportation, air. If we move to railway, the situation is completely different because there are many more contributions. And in fact, using railroads is probably the most preferred long mode of transportation for freight. So we see contribution both at strategic, tactical level and operational levels. All kind of Petri nets really are used, so I won't detail all of them. Regarding the strategic mode, the strategic problems, many problems have been addressed: collision avoidance, railway speed and route control systems, but also railway signaling and maneuvering management, the assessment of maintenance, and also life cycle cost analysis and risk analysis. So this from a strategic point of view. Instead, from the operational point of view, deadlock prevention and avoidance has been addressed. The dependability and safety of trains and the track allocation, which is of course an important issue for railroads, trains monitoring and dispatching, the control of level crossing, which is evidently also a significant issue, the verification of operations in stations and block sections, and the optimization of export operations. So you see many more papers during the last 15 years, with a peak in 2009. And again, this is one of the areas that are most addressed in the literature on freight transportation. And probably the reason why is that these problems are also very similar if we consider freight and passengers transportation, because really the unit in which they travel, so the wagon or the container, are basically the same thing from the point of view of the train transportation. So that's why probably we see many more contributions. And what we can say is that both kind of problems, so resource planning and performance evaluation and monitoring and control of resources, have been addressed, especially in using high-level Petri nets. In particular, I would like to mention color Petri nets that can be used for this kind of systems because they have a high descriptive power. Of course, they allow flight simulation for the detection of bottlenecks. They allow solving computationally complex problems in relatively short times for real-time control purposes. And they allow the prevention of deadlocks, for example, with the use of the generalized mutual exclusion constraints that were proposed by Dua, Di Cesare and Silva about 2 decades ago. Also, fuzzy Petri nets can be used because they can support modelers in representing knowledge-based rules to control rail traffic in case of anomalies and abnormal behavior, so disturbances and disruptions in a network. And I would also suggest the use of further extensions of high-level Petri nets. For example, colored hybrid Petri nets could be studied. A seminal paper here is the paper published by Jua and Seatsu in 2008 in the IEEE Transactions on Automation, Science and Engineering, which is exactly on supervisory control of railway networks using Petri nets. So I suggest you to read this if you are interested in this kind of transportation. The next mode of transportation that we can analyze is road transport. With road transport, not surprisingly, we see most of the contributions at the operational level, less contribution from the strategic level. In the strategic level, we see the study of route planning and optimization, logistics planning and supply chain management, especially, and risk analysis. Instead, the operational level problems are probably more interesting. A very interesting subject, especially nowadays, is the management of transportation of hazardous material. Of course, the rerouting problems, especially in large transportation networks, and then some themes that are actually also close to themes that you can find in passengers transportation. So freeway ramp metering, freeway speed control, and evidently also level crossing control, and others. Here you see all kinds of Petri nets that are used. And I would like to mention batched Petri nets that were used also by Professor de Mongodin, who I saw connected earlier. In this kind of mode, you see there has been a peak, I would say, at the beginning, I mean, 1 decade ago, but then the numbers are going down. And in fact, despite this great interest, especially for first and last mile transportation, there are not many contributions in this area. In particular, from the resource planning and performance evaluation point of view, we can use stochastic Petri nets, especially for the evaluation of the operational performance of emergency systems in the case of acts when there is transportation of hazardous material. And then colored Petri nets are also interesting because they allow route planning in the last mile. They offer the possibility to update the structure of the network at each change of the system, and in general to manage or prevent accidents and risks. And we can also use continuous and hybrid Petri nets to model and control both offline and in real-time road transportation systems. What has not been studied yet here is the use of high-level Petri nets for real-time problems, like, for example, rerouting in case of congested roads or delivery replanning in case of unexpected events. These are two important issues where contributions are still sought for. And I would suggest you to have a look at the paper by Kabashin that was published in Procedia Engineering in 2016. Another important means of transport are pipelines. Pipelines are used to transfer typically gas or oil for long distance. And so this subject has been studied, especially in the latest years, both from the strategic and operational point of view, with several types of Petri nets. They are used mainly for refineries. So they have studied planning of cleaning operations, optimal route planning, risk analysis, and the analysis of the interdependencies in complex systems. From the operational level point of view, the scheduling of crude oil refineries operations have been addressed, and also the refining of scheduling operations. Here you can see the graph of the contributions in the last 20 years almost. And as I mentioned before, most contributions are on refineries. And so summing up for this type of mode of transportations, logical Petri nets have been used to plan operative procedures necessary to transfer gas or oil in the pipeline. So they have been using structural analysis in combination, structural analysis of Petri nets in combination with mathematical programming techniques. This is really a common approach. And also they have used stochastic Petri nets to evaluate in advance the effectiveness of emergency plans and the behavior of the system in case of critical situation, and higher level Petri nets for risk evaluations. And finally, colored and hybrid Petri nets have been used for the computation of shorter paths in the pipeline transport to find solutions for these extremely complex systems. What is missing is the application of fuzzy Petri nets to this system. And I suggest you read this paper by Guo and others in 2016 on the Journal of Natural Gas and Science Engineering that you will find referenced in our paper again and in the slides. Now, from my point of view, the most interesting mode of transportation is, of course, the combined mode of transportation. So the multimodal and intermodal transport that has been born, I would say, with the writing of the White Book by the European Commission at the beginning I would say around year 2000. So in this type of transportation mode, basically we find all transportation modes combined. And so we find all problems as before combined, both at strategic and operational level. There have been studies on delay reduction in motor road terminals, the dimensioning of truck waiting areas, which is of course a very important problem for big terminals, and in general resource planning for terminals, and finally the evaluation of the efficiency of these terminals. From the operational point of view, route generation has been studied for multimodal transport, the control of container handling resources, because they can be significant bottlenecks since they typically have to be moved by men. So you need human labor here, and the optimization of intermodal terminal activities, and in general the analysis of reliability of these kind of terminals. And also here you see all types of nets, time Petri nets, stochastic, hybrid, and hybrid with fuzzy. And as you can see, you see a peak of publications in the last 5 years. And as I mentioned, this is not surprising because there was the white paper on transport that was published in year 2001, and then there was a second edition 10 years ago in 2011. Also, regarding the intermodal terminals, there is a particular class of papers that studies the handling resources, the automated handling resources, in particular automated guided vehicles, and the decision problems that are related to these type of transportation means. So we found that this was a class worth considering, because we found several applications with different types of Petri nets, and the problems that were considered, of course, were operational level problems, because we're talking about the actual handling of the freight inside the terminal by the AGV, and problems that were tackled were fault detection and identification, scheduling, collision avoidance, and dynamic dispatching and routing. And here I would say that there is still room for a lot of studies, especially considering the studies that have been already done in the internal logistic area for manufacturing systems. Of course, this is a bit different because here we're talking of terminals, so there's no manufacturing at all, but still most of the findings that have been applied and have been done in manufacturing systems can be easily transferred or transported, to use the transportation term, to this field. So summing up, for multimodal and intermodal transport, the problems that are addressed are both resource planning and performance evaluations, and in particular simulation and performance analysis, and then also monitoring and control of resources with timed or stochastic time Petri nets to address the prediction of faulty behaviors and even real-time monitoring, and the dynamic dispatching and routing of AGVs. They have been using also color Petri nets, especially for path assignment to avoid deadlock. I would say that what is missing here is still the larger use of high-level Petri nets to capture the complexity of the system and simplifying representation, so solving real-time monitoring and control issues. In this context, you will find a paper that has been published by my group in 2016 on transaction on automation science and engineering, and also a paper by Gudeli and others in 2012 on another journal. So you can have a look at those if you are interested in this subject. And now, for the few minutes that I have remaining, I would like to talk a little bit about some practical applications that we have studied with my group. First contribution can be found exactly in the paper that I was mentioned in transactions and automation science and engineering, and it's the modeling of the Trieste port. The Trieste port is quite interesting because basically it's an intermodal terminal. And as you know, Trieste is on the sea, but it also has a problem of space. I mean, there are the mountains that are nearby, so the terminal has to be very efficiently managed because there is not much room for extending resources, basically. And so what we did was to model the system. Here you see the logical scheme. So you see the presence of railway, of course, transportation by water. And then you see also the road, and you have actually several access roads, even some highways with a top booth. And as you can see, there were several different types of transportation units that are allowed in this type of terminal. So here you can see the model that we realized. The nice thing about this kind of models is that you can use basically some building blocks like a Lego, you know. So you can compose all the building blocks together that we presented in our paper, and then you can compose them together. So you have a modular structure that basically repeats the actual structure of the logical scheme. We propose some interfaces between models that we call the routing nets. Events can be modeled stochastically very easily. So you can see, of course, the stochastic transitions here. And then we also applied the GMAX proposed by Jua and others to control the system. For example, you see here a monitor place. So what did we use this for? We use this, first of all, to simulate structural changes. So what would happen if we increase or decrease the waiting areas dimension for straight or semi-trailer trucks? If we decrease, do we arrive at congestion? If we increase them, do we have resources that are underutilized? You know, problems like this. And of course, also simulation of operational changes. So we simulated, and then this has actually been applied, implemented, the introduction of technological improvements. So the ability to book for containers the actual yard space before the truck arrives at the port, because as I mentioned, space here is really an issue for this kind of port. And of course, performance indices are an important issue. We propose some of them. So average free capacity of the intermodal terminal, average free capacity of the last highway portion, because this basically is related to the congestion of the entrance in the port, and then throughput of stochastic transitions between highway and terminal, and between terminal and seaport, because this again is related to congestion and to how quickly operations are being done. We did a similar thing in the same paper for another real intermodal terminal, which is actually in Bari, the city where I live, and it's been managed by GTS, which is probably the biggest container handling company in Italy. And here, as you can see, basically you have a combined transport from roads to railway and vice versa. And again, also here, the problem that we studied quite accurately was the management of the yard, because before our investigation, basically the yard was managed manually. And of course, if the manager of the yard was not there for some, familiar or personal reason, then there would be basically chaos in the whole system. And here, exactly as in the previous example, you see the model of the system, which is quite modular. Again, you can reuse base modules like in a Lego game, and there are interfaces between modules and stochastic events modeling. And we did exactly the same study as before, so both simulation for the variation of, especially for the variation of container flows, because they have some seasonality issues. They have some moments in which they have peaks, so they wanted to study what happens when there are peaks of trucks arriving, especially of trucks arriving at the terminal. And of course, the performance indices that I mentioned before, in particular with attention to the yard storage area, which was the one that we had to study accurately. What is interesting is that for this same terminal by GTS in Bari, we did a further study that was published in Robotic and Automation Letters. Actually, I'm very proud because this was the very first paper that was published on robotics and automation letters. So it's like volume 1, number 1, page 1, something like that. So I like that. And so it's the modeling of the same system as before, the GTS terminal in Bari. But what is interesting is that we applied here first order hybrid Petri nets that have been proposed by Giua, Balduzzi and Menga a few years ago. These are quite nice hybrid Petri nets because they can be represented by a first order discrete time system, by discrete time equation. So they are quite easy to implement in a simulation software, in a computation system, in a computation platform. And the nice thing is that, again, the system is hybrid, so you can model continuous and discrete elements. So what we did was basically fluidify the container's flow. And this allowed us to really simplify the model. But also what is very nice is that with this kind of Petri nets that were proposed by Giua is that you can apply control policies based on objective functions optimization. So just to give you a flavor of this, you can basically define some optimization problems in which your objective function represents the system behavior using the instantaneous varying speeds of transitions. And so we defined two different control laws, but of course others can be defined depending on the system and what you want. In particular, the maximization of the outflows of the terminal. So we considered all the transitions that were in output from the intermodal terminal, and also the minimization of the yard storage area. So in this case, we considered the transitions that were connected to the places modeling the yard storage area with, of course, several performance indices. And so we could be able to basically decide the flow of transitions, so these firing speeds, in such a way as to maximize the outflows of the terminal or minimize the residual intermodal transportation units, so basically the containers, let's say, in the yard storage area. So this type of approach is quite interesting. So heading on to the conclusions, I have presented a brief overview of the use of Petri nets for freight transport decision problems. In fact, Petri nets are an important tool for structural and behavioral analysis of transport systems. They are quite a valid support for managerial decisions because they are able to simulate the system and also they are scalable and modular. The most addressed areas in the field of freight transport are, I would say, intermodal freight transport and rail transport. Instead, in the context of water and multimodal and intermodal transport, the employment of high-level Petri nets is limited. There is also a lack of contributions in the air and road transport context with Petri nets. And in general, scientific contributions do overlook the possibility to employ hybrid or continuous Petri nets for control purposes, which is very interesting, as I just showed, because with the fluidification, you can really simplify the system, and in the case of first order IP Petri nets, enforce some control laws. So what are the future developments there that can be done? First of all, clearly study more air and road freight transport, where there are not many studies. Also investigating the potential of high-level Petri nets for this type of problems, especially for multimodal and intermodal transport, where the system itself, the terminal, is quite complicated. You have a very high number of resources, and so high-level Petri nets can be very useful. And again, enhancing the use of hybrid or continuous Petri nets for optimization and control purposes, where again the use of fluidization may really simplify the problem and allow at the same time to enforce some control techniques. So this is all. Thank you for listening to me, and of course I am happy to hear your questions or comments. Thank you.
Thank you very much, Mariagrazia. It was an impressive survey of a quite wide range of literature. So in that sense, your proposals for classification are certainly interesting. And I particularly like the identification of not yet covered topics, which is, of course, a contribution in itself offered to the community to have a look at it. So now is the time for questions. So in the audience, I would propose that if you have a question, either you raise your hand in Zoom, or you can write it in the chat if you like. Or you can speak out if you are the first one to ask a question. Anyone in the audience? I do have a question or two, but I don't need to be the first one.
Don't be shy.
Ah, I see. Stéphane. Hop. Voilà.
Hello.
Yes.
Hi,
Hi.
Stéphane. Nice to see you.
Good to see you. Yeah. My question is what, there's presumably a lot of work on freight transportation in the operations research community not using Petri nets. So what's the distinguishing contribution of the literature that you surveyed? Is it the capabilities of the Petri net modeling that captures, better capture the concurrency in these systems that as compared to the other types of models, which I don't know what they look like, but
I would say, I mean, what you find in the operational research community is typically, of course, mathematical programming. So in the case of Petri nets, what I like, but I mean, I'm probably biased, of course, because I like control. But what I like is, first of all, you see the dynamics, you really see it. And that's very nice because these systems are evolving systems by definition, of course. You see the dynamics, you can see it in simulation, you can see the bottlenecks, and that's very nice when we're talking about these systems where, I mean, cost is an issue, especially in intermodal terminals, for example, and where a resource more or less can really do the difference. And where, for example, you can have, you know, priority on freight, like because it's freight that after 1 or 2 days it expires. I'm thinking also of medications, or simply when we were talking with the managers of the terminal in Bari of GTS, they plainly said that they have some clients that have priority because they pay to them a lot of money, and so it's important for them to see exactly what is happening to them, because maybe then they have a client that sends 1 container and the others they send thousands of container in a month. So of course for them it's really a difference. So definitely simulation, and I mean dynamics, seeing the dynamics is very important. And of course, as I mentioned partly towards the end, is control, because with Petri nets you can enforce control laws. So not only GMAX, for example, that's very nice, especially for you know, for controlling resources, but also all types of control, and I would say more optimization purposes. And in this matter, I find that the contribution by Alessandro Giua with first order Petri nets, with first order hybrid Petri nets, is really exceptional, because of course, it's a model that is simplified because it's hybrid, but on the other hand, it's very, very nice to apply it. You can really play with it with all sorts of control rules that really depends on the manager of the transportation facility. So I think there's a lot that can be done there. We've done a few things, but there's really a lot of space there. And if we can convey this to, you know, the actual managers of these facilities, that would be really, really nice. We did it a little bit with those with whom we worked, but I think there's a lot that can be done there.
Okay, thanks.
Thanks to you.
Okay. I saw that Isabelle de Montgodin raised her hand, but now I don't see her hand anymore. Are you there?
Well, she wrote in the chat that she had to go.
Ah, yes, okay, but still
and she asked if there is some contribution on energy transport. There was a couple of papers on this issue, and of course this is really an interesting subject, because of course you know, the crossing of energy and transportation, especially now with, you know, sustainable mobility and so on, it's really an interesting topic. So if you have a look at our paper, there is a couple, I mean, at our survey, there is a couple of papers that are referenced on this, but definitely it's an interesting subject where there is space for work.
So I'm going to ask a question just to raise more questions, hopefully, unless Bengt, would you like to ask a question? I see.
Yeah. Okay.
Go ahead, please.
Thank you. Thanks to Mariagrazia for a very interesting talk. So you say that, if I understand you correctly, that the graphical model of PetriNet is really useful. And why I question if that is really the case is because when I've discussed, for instance, with Manuel Silva, I mean, PetriNets are good for the flows. Mm-hmm. But when you come to the logics around these flows, you soon get what he expressed as the spaghetti. I mean, there are a lot of arcs back and forth. And the question is really, are these arc really telling you anything? Wouldn't it be better to have some logical equations for describing that? You know, I propose PetriNets with shared variables as an alternative. So let me hear what you think.
Yeah, first of all, hi, Bengt. It's nice to see you. And well, you know, this is like a party with friends for me. So it's really nice to see you all. Now, regarding this, what we have tried to do, and I think that is the answer to your question, is to really, you know, define the PetriNet following the actual physical and logical scheme of the system. So of course there are an infinite number of PetriNets that are equivalent and that have the same dynamics. So you're right, it can be done in a spaghetti way, definitely. But on the other hand, if you use modularity, as we try to do for our systems, for the systems that we studied, then it's really nice, because first of all, you can see congestion. By simply looking at the tokens, you can see if there is a resource that is underutilized or overutilized, so maybe you need to double it. It's really visual, let's say. So and that's quite nice from my point of view. You can, of course, then get information about markings and, you know, firing of transitions and blah, blah, blah. But what I really like is that you can see the critical resources in the system. And this is very important in freight transportation, because, as I mentioned, there are issues of cost, first of all, but also of priorities. And these can be typically solved by increasing resources. However, you have to convince the managers of this facility to invest their money. So because it's easy to just say, let's double all the resources. Of course, you can't do that. And so this kind of tool is very nice from that point of view. And that's, again, that's what we did in Bari with the GTS terminal, and it worked just fine. So I think that's the main point, using modularity. And then with modularity, you really see the dynamic of the system, or even of the subsystem, and then the congestion and the critical resources of the system.
Okay, thank you. I mean, my point is that the model, or the tools that you're using for the more algorithmic part, like optimization and different types of logical evaluations, they are mostly based on some kind of reachability search or branching bound search in the optimal solutions, and they are very much in the operation research area too. So it's good to hear that you have some good examples on where, so to say, the graphical description of PetriNets is really useful. So I want to come back to you on that. So thank you very much.
My pleasure. My pleasure. Thank you, Beth.
So I'm going to ask one of my questions before I forget.
Please, Eric.
So you were saying that Petri nets are scalable and very expressive, and you showed it in a very convincing way. But if I understood well, the way you use them is essentially in description and simulation. But I was wondering, because another kind of use of these formal models is verification or controller synthesis. And then I would be afraid that, of course, it would be more complicated to handle large size models. Do you have a notion of order of size of the models which you are using? And how do you think they would be amenable to reachability analysis? Or
it depends on how deeply you want to model your system. So I totally agree with you. If you go into verification, of course, then you can have a state explosion problem, and that's an issue. But on the other hand, what you can do is use, as I mentioned before, continuous or hybrid Petri nets. So you can make fluid some parts of the system. You lose information. That's obvious. So that's the cost of this operation. But on the other hand, you gain in lesser dimension. But most importantly, from my point of view, is that you can apply some control techniques, for example, with first order hybrid Petri nets. And that's nice. And then once you have controlled the system and you have done your choices on resources, you can even do a second level study of that portion, for example, of the system with a more insightful net. So remove the continuization or fluidification of that part and make it discrete and make it more precise. That's also something that we have done actually in the field of manufacturing systems, but it's an easily and viable procedure also here.
Okay, I see. Thanks. I see a question in the chat by Philip W. Do you want to speak it out, Philip? If you open your microphone.
Whether my mic works. If it works, I can also speak it out.
I hardly hear you.
I can hear you.
Okay. First, thanks for the nice talk. I have a question on control of the Petri nets. Do you mean feedback control with it? And what is the measurement of the Petri net? So which part is measured? Is it the marking or what is it? And how do you influence the system? By actively firing transitions or by adding additional transitions and places?
Thank you for your question. As I really briefly mentioned, so I would suggest you read the last paper in particular that is in the slides, so the paper that was published in Robotics and Automation Letters. It's true that it's not really control what we're doing in the feedback control sense. It's more, I would say, optimization. In fact, what we do is we define an objective function in which we want to optimize, so to choose the instantaneous firing speeds of the transitions. And of course, choosing them means to take decisions on the events that are related to those transitions. So it really depends. I mean, it depends on the actual system. And then what we, so I would say that the control actions are so the inputs of the plant that is controlled are the speeds of the transitions, and the outputs, so what you observe, are basically the states. So in all the states of the system or all the states that you have defined in your Petri nets. So it's basically the marking of the places in which you are interested. So the resources fundamentally, because typically in this kind of systems, the places represent resources. I hope I've answered your questions.
Yes, this was what I expected. Thank you.
Thank you. But what I suggest is that if you're really interested in this point, I suggest that you read first the paper by Alessandro Giua on first order hybrid Petri nets, which is very, very nice and very clear. And then after that, you can read the robotics and automation letter papers that we propose for terminals. And I think that could be quite useful. Thank you.
I see that Kai has raised a hand. Go ahead. Ask your question.
Thank you, Mariagrazia, for the very nice and the informative talk. And there are many literature papers in the talk that I will like to check it out later. So my question is on a very small point that you briefly mentioned. Maybe you have a reference, but let me just ask you to describe a little bit more on the agent-based PetriNet. There was a place.
At the moment, I don't remember the actual paper, but maybe Graziana Cavone, who is connected, remembers it. Graziana, are you there?
Yes, I'm here. Exactly, I don't remember the name of the paper. It was reported in the slide, some reference. So practically we can provide eventually the name of this.
Yeah, we send you an email.
Sure.
Okay, perfect.
Sorry, but there were so many papers that we reviewed that it's a bit difficult to remember all of them. But we definitely will find it and send it to you, Kai, or to anybody else who is interested.
Sure, perfect.
Thank you.
I had another question of more of curiosity, maybe of opening, because it was interesting for me to see that you are so modeling with these Petri nets a variety of transportation systems. I am more on the side of, well, in part of my work of embedded systems, and I was wondering if it would be interesting to consider interactions between the controllers of these infrastructures and the controllers embedded in, I don't know, trucks, boats, in the sense that this might, well, make sense in the sense that these embedded systems are the vehicles which are going through the transportation.
I'm sure that this can be done for the operational problems. So for problems from real-time point of view, there surely is some connection that can be, employed because embedded control is real-time control. So yeah, probably for trucks, because one of the problems, especially, for intermodal transportation, but also for road transport, what happens is that typically the last mile, so first and last mile, is done by road. And what happens is that basically the drivers, they don't really follow what they're told. They do as they wish. So, I mean, this is an issue in Italy, and probably depends also from our character, which is a bit, difficult to control. But anyway, this is really more a social issue. So I guess that for this issue, it would be interesting to link, as you say, operational control and embedded control. There surely is something that can be done. So thank you for suggesting it.
Okay.
Oh, Graziana just sent on the chat the paper.
The reference, the answer to the previous question.
Yes, I see it. Thanks a lot. I'll check that out.
Okay. Is there another question? Yes, Stefan, please. Go ahead.
Yeah, sorry, me again. I have two quick questions. I don't know if you want to do them now or during the discussion in case you want to close. So does it matter? So my first question, you can decide if you want to answer them now or later. You talked about modularity of the models. So what coupling mechanism was it that, was it shared places, the technique you used to couple the different
yeah, basically shared places. Basically shared places. We proposed some very simple networks that we called connection nets, and yeah, it's basically two places. So we double the connection place and the transition. This way you can even control the transition, and so actually the movement of the resources from one subsystem to another. So the connection networks are very simple, but it's nice because then you can control the flow of transportation resources in the system. For example, if you have a gate, a gate, by simply a gate, I don't know, or the highway is not open all day, things like that. And that's so it's very nice to model this kind of things in a very simple way.
Okay. So my second question regards the simulation. Did you create your own simulation environment for your PetriNet models, or did you rely on some existing commercial or academic simulation?
We have used MATLAB. We use MATLAB when we can, and then so we wrote basically code in MATLAB, and then we did some graphical graphical user interface, but something very simple.
Okay, thanks.
Thanks
for the talk. Thanks, good to see you.
Good to see you too.
Okay, thank you. We are just a bit over 1 hour, so I think unless there is an urgent question, we can move on to the next part of the program. We can thank Mariagrazia again. I don't know how to clap in Zoom unless
thank you.
But I can do it physically. Yes, there are clapping interfaces. Excellent, very good.
Thank you.
So now what I propose is that I will open a few breakout rooms because traditionally there is this phase where people can go in breakout rooms and chat a little bit. I see that if I do 2 rooms, it's 12, 13 participants, which I think can be nice. So I will do that. I will open the rooms. The people will be assigned a bit randomly. And I guess that the main room will remain open and I will stay there with Mariagrazia. Voilà. That's it. So I guess that there are 2 rooms essentially. And we are into 1. Voilà. Okay.
I stayed in the main room.
Yes, me too.
We can go to another room later. Hi, Eric. How are you?
The people in the east are finding that it's becoming a little bit late. I'm afraid.
Yeah.
So, voilà.
Mariagrazia left. She joined another room, or
where is she? No, I see her in room 1. Maybe we should go in room 1.
I'll go to room 1 then. Okay.
Allons-y. Hop. Yes.